Previously, we introduced some famous continuous distributions. And now in this video, we're going to learn some new techniques to create new distributions from those we already know. So in this section, the title is Creating New Distributions. The first technique is called the scaling. Sometimes, we also combine it with shifting. So shifting and scaling are often combined to create a new random variable. Here we have one example. So if you start with a Weibull distribution, you can scale it by the second parameter lambda to get y. This y has the so-called standard Weibull distribution. This is not exactly a good example. So let me give you another example. So suppose I have a normal distribution with mean, mu, variance, sigma square. Let me define a new random variable y by x minus its mean divided by its standard deviation. And I believe at this moment, everyone knows this is a standard distribution with mean 0 and variance 1, right? This is so-called standardization. To create this new random variable y, I applied subtraction, which is shifting. I applied division, that is scaling. So I applied the two skills or two techniques to get this new random variable y. Okay, so this is scaling. Of course, we can apply some more complicated function on top of it. So here, what do you think of is it's a linear transformation, right? It's an affine. So what I actually did is use a constant times x, and then I minus another constant. This is a linear function. Okay. We also know something more complex, like a power function. We can apply power function down here. Assume you have an exponential random variable x. So this is exponential. Now we define y as x to the power of 1 over alpha. So this is how I define new random variable. I apply a power function with power term to be equal to 1 over alpha. Then obviously I get Weibull distribution, right? That's one of the things I mentioned when I introduced Weibull distribution. In particular, if you focus on its survival function, okay? The next one is exponential transform. Since we know the exponential function. So in this case, you start with, let's say you start with normal. This is a normal distribution. And you can apply exponential transform to y. So y is the exponential of x. If this is the transform you apply, y will follow the so-called log normal distribution, which is a dominating choice in mathematical finance. People use y to model the stock price or the stock return. It follows a log normal distribution. It's nice because it's exponential, right? You want to model the price as something non-negative. So when you apply the exponential transform, you get a non-negative price, which is good because stocks are. So when companies they issue stocks, they have limited liability. So they can declare bankruptcy and the price goes to 0. It does not go to negative. So that's why log normal is more preferred to the original choice of normal distribution. By the way, when Basheria originally wrote his famous PhD thesis in 1990, he proposed to use a normal distribution to model the stock price. And then he was able to find the option price given that assumption, which was fundamental at that time. But here, then later on, people don't like the normal distribution, because if you apply normal distribution, there's always chance that something gets negative, right? If you don't like it, you can apply the exponential transform to convert it into positive values. Okay, so here is the result of the distribution. This is a PDF, and we have the result down here. So if you have log normal, means the log of it follows a normal distribution. This is the notation. Sometimes you may say people write this ln to denote this is log normal. In the textbook, the author simply use curricular CL. We have this results. So let me insert a page to discuss a little, which is related to what we did before. The first one I want to do is here. Okay, the power transform. Okay, so let's take a look to see power transform. So I start with exponential distribution. So x is exponential. I create y as the power of x to 1 over alpha. Okay, so it claims the distribution y follows is a Weber. Let's test. Obviously, x is positive, so y is also positive. Let's say alpha is greater than 0. What's this? Somehow I can't get 0. So let's do this. So let small y be anything positive. So this y is positive. The first step is to use the definition of y. Y is x to 1 over alpha, so less than y. Okay, the inequality is not about x, so I need to raise the power to alpha on both sides, right? So now it's a inequality directly about x, and x is exponential distribution. I know the CDF, negative lambda times y. Okay, this is very close to the CDF of a Weber. So if you forgot, let's go back to take a look at the CDF. Okay, so this is the CDF of a Weber. Okay, see this lambda is inside the power term. Okay, so it's inside, so the entire thing take to the alpha's power. If you go to what we have, it's close but not the same. So in order to get it to be exactly the same, I will need to get everything inside, right? So in order to get it inside, I need to, this is what I need to do, right? So that's why it is a Weber distribution with first parameter is alpha. The second one is this special term. So this is exactly what I just proved. So y is a Weber with alpha and 1 over. Okay, so this is the special parameter of the second one. Now let's talk about the log normal. Okay, and y is e of x. So here x can be either positive or negative, but y is always positive. So for any y greater than 0, let's calculate the CDF of big Y. So the first step is by definition, right? So the next step is to make the left-hand side be x. So I'm going to take a log. That is why I need this y to be positive, so I can take logarithm. So again, my x is standard normal. By the way, you need to know the CDF of a standard. This is a normal, not standard normal. 2 sigma square alpha minus mu square. If you write the PDF down a few times, you will naturally memorize. Okay, everything should flow somehow naturally from your mind. So this is nothing but definition. The next step is the key. Okay, so this is obviously the CDF of Y. So what is the PDF? PDF is the derivative of CDF. Okay, so I need to differentiate with respect to Y. So how do I differentiate? There is no Y in integrand, so that's a good thing. There's a Y somehow in the up point, but not in the lower point. So I need to differentiate this, the upper point, and replace X by this upper point. By the way, this is the fundamental theory of calculus. You should have studied or have learned this from your calculus course. If not, go back to review. It should be in any calculus textbook, right? So this is the PDF of a log normal distribution. So if you compare to 2.50, this is exactly what I just derived, right? So that's by definition and eventually by applying the fundamental theory of calculus. So so basically, the first type, like a transformation, is relatively easy, right? So what you do is you apply a function. So you start with a known distribution, x, and then you apply some function g to get y to be g of x. Okay, in this case, in the scaling case, g is just a constant times x. Okay, so you can think it as a slope times x, or even you add or minus a constant. So it's linear function, and then you have power function, then you have exponential function. That's what we did in the first part. Now let's move on to the second part. Second part is, well, most people have confusion with. It's the mixture distribution. Confusion comes from conditional distribution. That is, I would say, that is the most difficult part of elementary probability. So if you only studied probability once, let's say probability 1 or probability 101, it's unlikely that you truly understand the conditional expected value from it. In fact, I even had hard time understanding conditional expectation after taking measure theory. Okay, so the first time, I had a little issue. It was after many tries, conditional expectation starts to make sense to me. So I'm going to give my best to try to explain. But in the end, I will have examples. So, even you don't really understand the mathematics of it, you should be able to do the computation. So let's first follow the textbook. So let X be a continuous random variable with this PDF. So here, what's special is there is a parameter, lambda. So this lambda, you don't know. So lambda is unknown. Okay, and lambda itself is given by some different distribution. So that's why sometimes I prefer to write this as x given lambda follows some distribution. Let's say. So this is my preference, but the textbook usually does not put the condition down here. Okay, they put it in the argument. So, but again, it's conditioned on knowing lambda. If lambda is something we know, we know everything about the PDF. But right now, we don't know the value of lambda. In fact, we only have a rough information of lambda, meaning the information of lambda is contained in the distribution of lambda. So lambda itself is another random variable. It follows some additional distribution, which we know, luckily. and then we do the mixture. So you see, y is something we want to know, okay? But you start with x, condition on lambda, and then you give lambda a distribution, okay? So let me give you an example to understand. Let's say here I have an exponential distribution. So normally we just need to know the value of lambda, okay? But unfortunately, this can be, let's say, 5 or 10, okay? So I have two candidates. I don't know whether my lambda is 5 or 10. So what I do is I flip a coin. So let me flip a coin. If the coin turns head, I pick lambda to be 5. If that coin tends to be tail, I pick lambda to be 10. So do you get any better understanding from this example? All right. So we have an exponential distribution, but in this case, lambda, the parameter, it's something we don't know. Okay, but luckily we know this lambda can be either 5 or 10 with some probability. Let's say 50-50. So what I do is I flip a coin. If I get a head, I will take 5 to be the parameter. If I get a tail, I will take 10 to be the parameter. See, this is not exactly a single parameter anymore. Although in the original distribution, lambda is the only parameter, but I add additional uncertainty to the value of lambda. Lambda itself becomes a random variable, right? This is exactly a random variable. So in this particular example, lambda is a discrete random variable. It can take two values, 5 or 10, each with 50% probability, okay? In this chapter, we would like to study the distribution for lambda to be continuous, okay, in most cases. So let's say try another example. Let me give you another example. Let's say my x follows a normal distribution. Let's say my variance is 1. So I know variance, but unfortunately, I don't know the mean of this random variable or this normal random variable, okay? But I know it's something between 0 and 1, okay? And I know this is a uniform between 0 and 1. So which means in order for me to get the full information, my first step is to pick something from 0 and 1, okay, and it's uniformly. So there's an equal chance any number is picked. Once this number is picked, I know my distribution is this normal, right? So let's say in step 1, I get 0.1. In that case, my distribution will be normal with mean 0.1, variance 1, okay? But it is also possible that I may get the first step mu is 0.5. Then my distribution will be a normal distribution with mean 0.5, variance 1. See, so it's possible I get anything. So that's why when I discuss the probability, I need to consider all the possibilities for mu. Mu should run from 0 to 1. And then I study for a specific mu, what is the probability, right? So that's reflected down here, right? So you should consider everything for lambda first, for the parameter. And for the given lambda, then I have the distribution for x, okay? Let's take a look at an example. Example always helps because I wouldn't be able to really tell you the definition of conditional expected value, right? So let's assume x is exponential. Let the parameter lambda to be distributed as gamma distribution. Determine this new distribution. Okay, so what we do is you can think this as a two-step process. the first step is random sampling from a gamma distribution. So you grab a random number from this gamma distribution for any number. Let's say you end up with 1. So lambda is 1. Then your y will be exponential 1. Okay, then you try another random sampling. You get lambda to be 2. This time your y is exponential 2. So of course, the probability of getting 1 or 2 may be different. Then you need to discuss in the end what kind of random variable you have, because it is a random variable, right? It's not taking any fixed value. So you need to discuss in the end what is the distribution of this new type of sampling, right? So that's what we do. We apply this result. Okay, so we know the conditional PDF for x is given by this exponential, right? Because it is exponential. And we also know the lambda, okay? Sometimes we call this hyperparameter because this is the distribution of the parameter. This lambda is the parameter of x. So we call it hyperparameter. We know it's a gamma distribution. It's given in this form. So according to 2.54, this should be the PDF of y. So again, how do I understand? How do I possibly understand this result? So first of all, there's a little typo. So this shouldn't be y. This should be that should be y, not x. So now I want my big Y to be around Y. So technically I shouldn't write equal to, because in this case we have continuous, right? So continuous, you don't talk about the probability of Y equals Y because that's 0, but it helps. So how do I get the big Y to be small y? So first of all, my lambda can be anything, right? So I sample lambda from the distribution, which is from 0 to infinity. So this means I'm going to choose a lambda, okay? And here I want my lambda to take this value, small lambda. So once a small lambda is selected, what is the probability for it? It's a y d lambda, not dy, right? So basically, it's like a 2-layer of selection. I want my big Y, the Y random variable, to be small y, okay? And in order to achieve that, first of all, I need to consider all the possibilities for my hyperparameter. Okay, my hyperparameter can be anything between 0 and infinity. So let's figure out what is the probability that my hyperparameter to be small lambda. Because once I take care of that, I know my distribution of x, right? Then I study when my x will be equal to small y. So that's the kind of mixture, the secret behind it. So, and then it boils down to the computation, which I already did something similar, right? So you have an exponential here, you have an exponential here. You collect like terms, put them together, and think this as a new thing, right? So you can use something to replace them, and you will see what it is. You can easily somehow differentiate or put in. So here, lambda is the variable, right? So you have a power function and you have exponential function that somehow motivates you to consider gamma. What is gamma of this function, right? Actually, this is gamma alpha plus 1. Okay, so you try to connect with this, and you will be able to see the result after some change of variable, because when we define this, right? So now you can switch y to lambda, right? So that's why I ask you to consider gamma alpha plus 1, because I have lambda to the alpha, right? But it's not exactly negative lambda. I have something more complicated. So you need to use another random variable to replace this entire thing, right? except the negative sign, then you will get the new gamma function. So in the end, you have this. Okay, then you do a little trick. So you introduce another change of variable to use gamma to replace 1 over beta. Then finally, you will end up with this. This is nothing but the PDF of Pareto. So you can see by mixing gamma exponential, you will actually end up at a Pareto distribution. This is, well, at this moment, you probably don't see how valuable it is. If you study the sequential course, especially when you study credibility, you will see those mixing distributions. If you know the result, it really helps. In this case, it's gamma exponential. Well, both are continuous, so it's not that interesting. But later on, you will see one of them is discrete, the other one is continuous. And if you know the mixing distribution, that could be very interesting result for the later on chapters. This I believe I already did in chapter 1, right? I showed you the basic idea of so let me try it one more time, but not proof, okay? So I try to use some reasoning to help you understand the meaning of conditional expected value. So it will be somehow a naive example, okay? So let's say I have everything inside this box, okay? So it will be dot, 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 dot. So each dot represents a possible value for my x. Okay, it's in a chaotic shape. I don't care. I want to know the expected value of it. So how do I calculate the overall expected value of this random variable? So technically, I need to look at every single dot within this box, right? I need to know the value and the probability. So let's hypothetically say the x. It's if you see this in a two-dimensional space, well, you have x, you have y, right? So let's say x-axis is somehow the value. The y-axis is the probability. So then it will be the x times y plus the next point plus the next point, all the points, right? So this is one way to do it. So if it's a discrete, it will be xi times pi, okay? But I don't want to do it this way. So I want to do it another way. So in order to do it in a second way, so let's do some cutting. So let's cut it half. So let's cut it half. Okay. Then some points are located on the left-hand side. Some points are located on the right-hand side. Okay. So left-hand side. This is the conditional expectation. Conditioning on the points are located on the left-hand side of my cutting, my blue cutting down here. Okay, so I do something similar, right? Except now, okay, I has to be the left part, but this P is different. Okay, so let me put a special P because this is not the original P. This should be the original one divided by everything on the left-hand side. Because now I only focus on the left-hand side, right? So the probability will definitely change. If this is too chaotic to think of, let's say I have 2 points. Let's put it a little bit more, 4 points, okay? So each with 1 over 4 probability. So this probability is 1 over 4. So let's say 1, 2, 3, 4. Okay. Originally, how do I calculate the expected value? So it's 1 times 1 over 4 plus 2 times 1 over 4, 4 times 1 over 4, right? So you add everything together, it's 10 divided by 4, so it's 2.5. Okay. So now let me cut it half. I look at the left-hand side. How many points do I have? I have 2 points, right? So each with probability 1 over 4. So they are equal likely. So my conditional expected value on the left-hand side is 1 times, it's not 1/4 anymore, it's 1/2. That is because when I condition on the left-hand side, my new world only has 2 dots, 1 and 2, right? 3 and 4 are out, okay? They are not on the left-hand side. Now I consider everything on the left-hand side. So the probability will change correspondingly because this is my new world. My world is not 1 anymore. My world is half, right? So if my entire world is half, 1/4 is 50% to my entire world. So that's why it is 50%, 50%. So from here, I get is 1/5, 1.5. So for the same reason, I can do the right-hand side. So I have 3 and 4, each has probability 1/2. So it's 3.5 right now, right? So my conditional expected value on the left-hand side is 1.5. My conditional on the right-hand side is 3.5. So in other sense, let's say location, this is a random variable. Okay, in this very simple case, it can take 2 values, 1.5. What is the probability of my left-hand side? A quarter plus another quarter, so it's 50%. What is the conditional expected value of my right-hand side? Right, so this is a random variable. So if I calculate the expected value of this random variable, this is the inside, it is also a random variable. So obviously it's my left mean times the left probability plus the right mean times my right probability, 2.5, which is equal to the overall mean, right? So now, if you go backwards to see what is the true meaning of conditional expected value, it's basically you look the entire picture part by part, right? So here I look at the left, I look at the right-hand side, and then I combine them together. So it's all about how you average, right? At the beginning, we average for each point. So, and the weight is relative to the entire world, okay? So then I don't like it. The entire world is too big for me. I want something smaller to start, okay? Then I cut my entire world into different portions. So you can start with 2 portions because that is the easiest. Then I look at the left, I look at the right, and then once I know the average from each part, I combine the average together. Then I get the overall average, right? Okay, how do I understand the second formula? So we just explained the first one. How do we understand the second one? Variance. Variance is variation, right? It's variation to the middle. So let's say that the cutting line is the middle, hypothetically speaking. It is the case in my second example. Okay, so now let's use the second example to talk about variance. So what is variance? Variance is the square to the middle or to the mean and times by the corresponding probability, right? Okay. But now we cut into 2 parts, right? So our mean for each part changes. So this is the left mean. This is the right mean. Okay. So first of all, I have in-group difference, right? So this is half. This is also half. And I also have the in-group probability. So it's 1/2, not 1/4, right? So the first variation I calculate is the so-called in-group variation. So that is the variance within each group. Here I only have 2 groups, right? So what I do is given left. So this is the variance given right. Okay, so once I know the in-group variations, I need to combine them. How do I combine? Obviously, I need to do some kind of averaging, right? So I average them together. That is reflected in this term. So this is the, for each lambda, for each value of lambda, this is the in-group variation. And then I take the average for all the in-group variations, okay? But that is not the end of it. There's another layer of variation. That is, okay, I have my left mean down here. This is my left mean. And I also have my right mean down here. I also have the overall mean. So this has distance. This has distance as well. So I also need to study between group. Right? So right now it is the variance of each group mean to the central mean or to the overall mean. So what I do is I also need to know the variance of each group mean. So this together will give me the variance. Okay, so that is the, well, I'm trying to use layman's words to explain the conditional expected value and conditional variance. I can only hope it works. If not, just treat those as formulas, which I actually proved, right, in chapter 1. It applies to the result here as well. Let's do one more example, and then we will we can probably finish this this section. So here we have x to be let's say conditionally exponential. The hyperparameter lambda has a distribution of gamma distribution. By the way, we already know the mixture distribution is Pareto. Okay, but we still want to calculate, use the previous two results to calculate the unconditional mean and unconditional variance. Okay, so this part is easy, right? Because x follows exponential, so the mean is 1 over lambda. So although lambda here is a parameter, but still we just put it as 1 over lambda. So in order to calculate, we apply the Tauer rule. Right, so that's why I have this. Then I know the distribution of lambda, right? Then it's like I apply 1 over x to x. So it's 1 over lambda, then times the density of lambda. Okay, easily you can write this as lambda to -1, right? So you can combine to here becomes alpha minus 2. That motivates you to think gamma function of alpha -1, right? So with everything we do, we can, you do have this formula. So we know this ratio is 1 over alpha -1. That's why you have done here, right? So this is not too surprising because we know this is if you go back, we actually proved the distribution down here. So you can also use the result from Pareto to calculate the result. But here we want to apply those two famous formulas, okay? That is the unconditional mean. So next is to calculate the unconditional variance. So first we need to know the conditional variance. This is the variance of exponential distribution. According to our formula, unconditional variance equals the expected value of conditional variance. This is conditional variance plus the variance of conditional mean. This is conditional mean. Okay, so now we need to calculate those two quantities. So in order to do that, well, one part we already know. This part we already know, right? From this, okay. What we don't know is this part, the expected value of the square of the reciprocal. Well, there's no trick. We have to apply the definition. So luckily, you know, it is also in power form. So when you collect those, is lambda to alpha -3. That motivates you to think about the gamma function of alpha -2, right? And from alpha to alpha -2, well, you apply the you apply this formula twice, right? You go to alpha minus 1, then go from alpha minus 1 to alpha minus 2. So you have two factors coming out from it, okay? Then you get the beta should be square at the bottom. Then we have the final result for variance, right? So finally, they have this quick point. You can get the same result by applying the mean and the variance formula of a Pareto distribution. The last part is splicing. Splicing, it's not that important for us, okay? And somehow it produces quite a lot of confusion between mixing. So people always people often, get confused between mixing and splicing. So first of all, let's take a look at the splicing. So splicing is to splice the entire region, let's say from 0 to infinity, okay, into different regions. For each specific region, there is only one PDF, okay? So basically it goes like this. Previously, we have also many choices, and they can happen like overlapping, okay, in the sense of mixing. But when we study splicing, so we have here k different PDFs, but they never overlap. So let's say let's put a specific value. Let's do not do the general case. Let's separate this into, let's say, 3 regions from 0 to 10. So I have F1. So from 10 to 20, I have F2. From 20 and beyond, I have F3. They do not overlap. So although my X1, F1 here is defined for the entire 0 to infinity, but I only use the portion from 0 to 10. The same F2 may be defined for 0 to infinity, but I only use the portion between 10 and 20. Same for F3. That is not something I have for mixing. For mixing, each distribution can be used for the entire region. So it can be for anything. So for the same F1, F2, and F3, I can do another coin example. Let's say this time my coin has 3 faces. Say 1, 2, 3. So if the face 1 shows up, I use F1. The probability is 1 over 3. If phase 2 shows up, I use F2. The probability is 1 over 3. If phase 3 shows up, I use F3. The probability is 1 over 3, which means the entire 0 to infinity of F1 is used if phase 1 shows up. So if the phase 1 of the coin shows up, I will use the entire part of F1. If phase 2 shows up, I will use the entire graph of F2. If phase 3 shows up, I will use the entire graph of or entire part of F3. That is mixing. However, in the case of splicing, only one part of F1 is used. It doesn't matter what the face of coin shows up. There's no coin. So here it's already known. I know according to the value of my X, not to the result of coin. That is why mixing is more complicated, because there is additional layer of unknownness in there. So there's additional uncertainty which comes from the result of the coin. But here there's no. I just need to pick the value of X, then I know which F I use. And I only use a specific portion of that F. For example here, only 0 to 10 matters for me for F1. Okay, the rest I don't care because I don't use, right? So I don't need to know the probability of F1 at 20. I never use. But in this case, it may be used, right? There's no way you rule out anything, right? So if you want to know the probability, it actually depends on which phase turns out. So you need to consider for everything, right? So you need to condition on coin one, phase one turns up, so you use F1. F1 can be anything between 0 and infinity. Okay, the same. F2, the value can be anything between 0 and infinity. The same for F3. But when we consider splicing, only one part is used from F1, only one part is used from F2, only one portion is used from F3. So it's entirely different, right? Although there is something um, inside, you can connect them. That is from the expectation. Sometimes, they can be the same, for mixing and the splicing, okay, in certain cases, okay? So when we draw the graph, it still is more obvious. You see, we have one part, okay? So this is F1. We have another part, which is F2. I mean, this is MATLAB or some other software. So you see this part. So actually, this does not exist, okay? So it's a jump, but the graph does not really handle the jump. So they must connect, use something smooth. That's why you see the vertical line. But it's basically, you just have three pieces. Here is F3. You see, so F1 might just continue. So this may be the shape of F1, but we don't need everything down here, right? So we only need the end to be at 1. The rest we simply don't care. So that's splicing. We do have example, but I leave this to you. Okay, it's not entirely difficult to solve this, and I leave this example to you. It's the truth is it's not that important. Mixing and transformation are way important. Let me end here for this section. We will continue in the next video.